All right. So k-means clustering is an old, extremely simple technique, extremely effective at sorting data. So let's make a data set. This is going to create another data set using pseudo-random points. And it's going to make a data set containing several blobs of points over here and two dispersed blobs of points over there in two dimensions, x1 and x2. So this data set is designed as 5 clusters, and we would just like to sort them into those 5 clusters. And the k-means model does that. So here's the code that will make a k-means model, and we'll see how this works. All right. Okay, so you see it worked pretty well. It's chosen these decision boundaries. Everything in here, it calls that group, that group, that group. It's clearly divided the thing into 5 groups, and it's done pretty well. It's done about as well as you could. So it works, didn't take very long, and it's pretty nice. So let's see the algorithm. This is done in an iterative process, and if we run this, we're going to print out the steps to get us there. I got to use the keyboard to paste. All right. All right. So first you choose random locations for the centroids. And as you can see, these 3 are pretty close to the center of something. These 2 are pretty far off, and it's just random. Now you label the instances. This is the k-means algorithm. So you label every instance, every item of data with the label of the nearest center. So all the ones near here are considered yellow. All the ones near here are considered green. These ones are still considered green because they're closer than they are to that one. That's it. So that's all you do. You take all the ones near your centroids and label them. Then you recalculate the center. Move to the center of the ones in that group. So this one here started randomly here, but it found a bunch of dots over there, so it moved over to closer to those dots. Then you just repeat the process and repeat the process. This is like dropping a heavy ball on a trampoline with a bunch of nuts on there, and as it falls, it makes a dip and creates these clusters. So that's all k-means does, and as you can see, it's a very simple algorithm. You can easily do it without a lot of computing power. So that's fine. You see the first few examples here as it quickly narrows down and does a good job solving it. All right, that's the algorithm. Now, the problem is sometimes you have bad starting values. Now, remember, we're doing a nice thing here, very handy for teaching. We're using pseudo-random values that are predictable because we seed them here. So if I change the seed to another value, you'll just get a different random starting point. And if you do that, I just tried different ones, I think, until I found one that would have this result. Else it was in the book, I forget. Okay, so here it has a different start. It puts 2 of them over here, and it puts one here in between those 2. Now you're in trouble. Now when this one finds all the nearby ones, it finds 2 clusters and includes them both, so it doesn't really move that far. And over here, it's got 2 centroids there, and it doesn't have enough pull to bring them over here, so it's going to split this one in half. So now you're going to end up with a solution like this. These 2 clusters interpreted as 1, this cluster split in 2, and that's not a very good solution. That's the problem with k-means. If you have a bad enough start, it will fall into a local minimum that is not the real global minimum that you were looking for. So the solution for that is by default, k-means will automatically run 10 times and take the most popular one. So that's one way to overcome this problem, that because these conditions where it fails badly are not the most common conditions for most data. Now here's another problem, like what we talked about before. If you change the vertical scale, that is really going to make problems. So if I do this, this is just going to take the existing data and multiply one of the parameters by 10. So it ends up looking exactly the same. The only difference is this is now going up by 10s and this is going by 1s. So I've just changed the scale of one dimension. Now, if you fit a k-means model to the scaled data, you're going to get a weird, disturbing result. So now these are the 5 groups. This is clearly not what we wanted, but it's what you told it because you told it that vertical errors count 10 times as much as horizontal errors. So it is better to make a stripe here so the vertical error is small and accept a huge horizontal error, 10 times bigger. This is what happens when you have the wrong scale on your data. So that's an issue I mentioned before when we talked about that California population data. You have to consider the units because the math just calculates the distance between the predicted value and the real value, and it uses the dimensions you give it. So if you don't scale things properly, you're not going to find the right answer. So now let's try fitting something that is not nice, simple Gaussian clusters. So here's another one of these moon-shaped data sets. We used this a few times just to show an example of a more complicated problem. Okay, so now we got blue ones up here and green ones down there, and the border between them is this curve. So if we use k-means on that, if we have eight, we're going to fit a k-means model with 8 parameters, and if you do it, you'll get this result. Now, the textbook says this is a terrible result. It didn't give me one cluster here and one label there. In my opinion, this is not bad, but I think of a 2-stage model. I would do this, and then I would say, take these 4 clusters and call them blue, and take these 4 clusters and call them green. So I would say this is a useful result, but to be fair, it hasn't completely solved the problem in one pass. And that's because k-means does not have the ability to change the shape of the group. It just takes the distance to the centroid, so it is only going to work for groups that are basically symmetrical and circular. If you have some other weird shape, it's not going to naturally group those items together. But here's a use of this, and here's an example of why this is extremely useful. And this helps explain how you can use unlabeled data to train your model. So here is the digits data set. We're going to get the whole thing, and it's going to print out the first 50 images and the first 50 labels. So I've got a data set which has, I think, 1,797 images. And I print the first 50 of them here. So here's the first 50 images, and here's the first 50 labels. And they seem to have the first few pretty much in order, but the last one is 8417. So humans assign these labels. Okay. Now, suppose I didn't have labeled data, but I had data I just downloaded from the internet or somewhere. And humans have to label it, and I have to pay those humans to label it. I really don't want those humans having to label thousands and millions of images. That's going to be too expensive. Is there a way to short circuit that? And there is a way to make a shortcut there. But first, let's make a model. Here's the apparently perfect model. This data set of 1,797 images has already been labeled by somebody else. So if we take advantage of the whole data set and train the model on it, I guess we're only using 1,400 of them for some reason, doesn't matter. Anyway, so if you train your model on 1,400 labeled items, then we'll see how accurate it is. And it'll come up eventually. Let me smooth this over a little. But there, it shows you 90.68%. So it gets 90.6 of them correct, 6% of them correct. So that is essentially perfection. If you had paid somebody to label all the data, that's the best you could do. Now, suppose we only labeled 50 of the data items. If we just take the first 50 items, the same one you saw in that picture a while ago, and we train a model using only 50 images, you would think that's got to be a lot worse than using 1,400, and it is. You only get 74.8% of it right. So that's vastly inferior. All right, but now what you do is you use k-means to cluster the images together. So I'm doing unsupervised learning. I'm not going to use the labels, but I'm going to take all the data and just fit it into 50 clusters using k-means. So I find images that are similar and put them together. And then I show the 50 representative images. These are the images closest to the center of each cluster. So these represent the types of images that exist, the archetypical images. And now humans can label them. You can manually label these 50 images, and here's code that includes these manual labels of those 50 representative images, and then you can train it on just the representative images. This is essentially what focus groups in politics try to do. They try to find people that will represent the voters and examine them and say this person's opinion represents what we think a whole category of people would vote, would say, think about these candidates and such. So now, retraining on just these 50 images, we've gone from 75% correct up to 85% correct, which is pretty good, but not as good as training on the whole labeled data set. But here's what we can do. We can take these 50 labels and propagate them to all image instances. So now we've labeled groups, so pretty much like this. We've looked at the image here and figured out what it should be. And now we're going to take everything in that group and just give it the same label. So we're not going to pay a human to label all these instances. We're going to just label them with the label of the centroid near their group. So after that, we'll have labeled data, although the human only labeled 50 of them. We've now propagated the label through all of them, and we'll train the data on the whole data set with that propagated label. And now we get up to 89.4%, which is almost as good as the entire unlabeled data, which was 90 point something percent. So we got a lot better, but now we can do even more. The last step is we can remove the outliers. And if you consider this example up here, we've now propagated, let me go back to this one, probably the easiest way to see it. There. We have now propagated the labels. I'll go up to there from here. We've taken the centroid and we labeled all these with a label applied to that centroid. But there are ones over here where it's really not clear if they belong in this group or that group. It's probably not really accurate to apply this label to that image up there. Maybe you should be applying this label. So what would be best would be to find the outliers and remove them, not use them to train, because we don't really know what the label is, and a wrong label is bad. So let's just take the ones that we've accurately labeled and train on them. All right, and that's what this does. This will remove outliers. It will take 99% of the dots and preserve them, but it will throw away the 1% of images that are farthest from centroids. And now you get 90.9%, which is in fact better than training on the entire data set, although it's just in the noise. That was 90.6 or something. So that's a very important technique to see. This is how you take unsupervised data and efficiently turn it into supervised data for further training. This is one of the many techniques. All right, that's what I wanted to show you with k-means. Stop recording in that.